to chemistry AS and A levels. This is going to be a quick examination revision. So let's get started with periodicity. Okay, periodicity is a study of trends across a period, and we take a look at period 3 for AS levels. And the trends we'll be looking at are atomic radius, ionic radius, melting and boiling points, chemical bonding, which consists of reactions with chlorine, reactions with water, oxide and chloride properties, and their reactions. Okay, atomic radius, this is pretty straightforward. Across the period, the atomic radii decreases. The reason for this is the number of protons increase across the period. However, the shielding remains the same, so the electrons are added to the same energy level. Thus, they experience a similar level of shielding. Thus, as the number of protons increase, the effective nuclear charge increases, and the attraction between nucleus and the valence electrons are larger, or the attraction per electron is larger. This leads to a more compact ion. This is pretty straightforward. This is a graph that you might be given to compare with, or even describe in your examinations. Next up is ionic radius, which increases and decreases for metal ions. Metals form cations by losing their valence shell electrons, and non-metals form anions by gaining electrons. Cations by themselves are isoelectronic, and the anions themselves are isoelectronic. That means that all cations in the period 3 will have 10 electrons, and all the anions will have 18 electrons. All right. For metals, the ionic radii decreases from sodium to aluminum. From sodium to aluminum, the proton number increases, but the number of electrons remains constant at 10 electrons. Thus, the attraction between nucleus and valence electron is higher, and the ion gets more compact. For non-metals, the radii decreases from phosphorus to chlorine as well, because the proton number increases. However, the number of electrons remain the same, which is 18. Thus, the attraction between the nucleus and the valence electron is higher, and the ion is more compact. Just take a look at this graph. I hope you guys can understand that. It decreases from sodium to silicon, and then it would increase because there's a difference of one entire valence electron, a valence shell, and they'll decrease again because the protons increase. Okay, melting points. From sodium to aluminum, the metallic bond strength increases. Thus, more energy is required to overcome attraction between the cation lattice and the sea of electrons. Basically, the cation gets smaller, and then the number of delocalized electrons increase. In sodium, 1 electron is delocalized, in magnesium 2, and in aluminum 3. So the metallic bond increases, and thus the metallic bonding strength increases, and more energy is required to overcome it. Silicon is an outlier over here because it has a giant covalent structure with strong covalent bonds between atoms. Remember, it's between atoms and not between molecules, and it's a giant covalent structure. And remember, it's a covalent bond, not intermolecular forces or van der Waals. Just remember that. For non-metal atoms, they're held together by weak van der Waals forces of attraction. The chemical formula from is P4S8 chlorine Cl2. Sorry, it's not Cl8, and argon, which is a monatomic element. The strength of the van der Waals forces depends on the number of electrons. The molecule with more number of atoms has more electrons. So in this case, sulfur has the most, followed by phosphorus, and chlorine. Like I said, this is a typo, it's Cl2, and argon has the least number of atoms and thus the least number of electrons. So the stronger the van der Waals forces, the more energy is required to overcome the forces and separate the molecules. Hence, sulfur has an increase over here. So this is another anomalous point. So just take note of this when describing the trend. Increase from metals. There's a large increase to silicon because it's a giant covalent structure, then decreases because it's non-metals and they're held together by van der Waals forces. However, there's another increase from phosphorus to sulfur because sulfur has more electrons. So you can just explain it in that sense. All right, electrical conductivity. All metals conduct electricity, and silicon is a semiconductor, so it will conduct electricity. So just remember these 2 points, and non-metals do not conduct electricity at all. Okay, reactions with oxygen. So sodium is a silver gray solid which burns with a yellow flame to produce a white solid. The words in bold are the keywords that you need to have in your answer. As sodium, magnesium, aluminum are not transition metals, they will not be colored. So they will not produce any colored compounds. This will be a white solid, and it will be a white solid for magnesium and aluminum oxide. These are the equations that you need to know. Just it's not that difficult. You can just memorize them, or you could just form them in your examinations. Remember, the flame that's produced with sodium is yellow, and magnesium and aluminum produce a white flame. Sorry. Um, Phosphorus burns with a white flame to produce a solid, which is phosphorus pentoxide. It's much better to remember it with the name, and instead of remembering the exact equation. You can always reform the equation by just remembering the product, so it's not that difficult to remember just the product. So remember the name, or you can remember P4O10, however you like it. It's a white flame to produce a solid. Sulfur burns with a blue flame. Please take note of the color, and produces an acidic choking gas, or you can just write choking gas, but just check your syllabus. This is the equation. Just take note that sulfur is the only element that does not reach its maximum oxidation state when burns in oxygen. It forms SO2 and not SO3. It could take a while to take these down and understand all the colors that are there. Okay, so properties of oxides and melting point. So ionic oxides, we all know they have a giant lattice structure held together by strong electrostatic forces of attraction between oppositely charged ions. Instead of stating oppositely charged ions, it's much better to name them. You can write Na plus and O2 minus, or Mg2 plus and O2 minus, instead of stating oppositely charged ions, and they have a high melting point. The strength of the ionic bond increases across the period as the charge of the cation increases and the cation size decreases. This is similar to metallic bond, but in metallic bonding, it was dependent on the size of the cation and the number of electrons that are delocalized. In this case, the strength of the ionic bond, sorry, there's a typo, depends on the charge on the cation and the cation size decreasing. All right, silicon oxide has a giant molecular structure. There are strong covalent bonds between atoms of silicon and oxygen, which require a lot of energy to break. This is a similar explanation to why silicon has a large melting point over here. It's similar, giant covalent structure, and the bonds are between silicon and oxygen in this case. You don't need to know this. You don't need to know this, but one silicon is bonded to 4 oxygen, and one oxygen is bonded to 2 silicon. So it's just some side information if you'd like to know. If you like to look at the lattice structure, if they give you a diagram, you'll be able to identify it, but you can just take note of that. P4O10 and SO2, they have simple molecular structure, and they're held together by weak van der Waals forces of attraction, similar to as we have discussed already. P4O10 has more electrons than SO2 because it has no atoms inside. It has 4 phosphorus and 10 oxygen, while it has 1 sulfur and 2 oxygen. Thus, it has more electrons and has stronger van der Waals forces of attraction. More energy is required to overcome them. Thus, the melting point of P4O10 is larger. Metal oxides and their reactions with water. Metal oxides will react with oxides and their reactions with water. Metal oxides will react with water to form hydroxides or alkalis. So just take note of this. Sodium hydroxide has a high pH of 3 to 14. Magnesium hydroxide has a low pH because magnesium hydroxide isn't fully soluble, so it will not dissociate to form the OH minus ions. This is group 2 properties. We'll get to that later, but just take note of the difference in pH. Aluminum oxide and silicon oxide do not react with water because they have large bonds between the atoms. For silicon, it's strong covalent bonds, and for aluminum, they have really strong metallic bonds between aluminum and oxygen. All right, so that's why they do not react with water. Non-metals have simple molecular structure and form acids, as you can see. Just take note of sulfur. Depending on whether it's sulfur dioxide or sulfur trioxide, it forms either sulfuric acid or sulfurous acid. Sulfuric acid has a lower pH than sulfurous, and H3PO4 has a low pH as well. So just take note of the reactions. It's much easier to remember what the oxide is and what the final product is. Water is just added, and you can just substitute it in the examinations by balancing the equation. Amphoteric oxide and silicon 4 oxide. Aluminum oxide reacts with both acids and bases because it has amphoteric qualities, and amphoteric means that it reacts with both acids and bases. So with acids, aluminum will react with any acid. I just pick HCl because it's pretty simple to remember. It will form AlCl3, or if it was H2SO4, it will be Al2SO43, or and it will form water. So any acid will react, anything, but I just remember this as it's easy to remember. With base, aluminum oxide reacts with 2 NaOH and 3 H2O to form NaAlOH4. A quick way to remember this is just remember the final product, which is formed, is NaAlOH4. It's not that difficult to remember, but you will be asked to state these both reactions, or any form of this reaction. Aluminum oxide has multiple reactions with base. However, I find this the simplest and easiest to remember. It's 232. That's a quick mnemonic to remember is 232, and just to remember the three water is added. Okay, silicon oxide is a non-metal oxide. It has acidic properties, but because it's a giant covalent structure, it does not is rather unreactive. However, with concentrated and hot NaOH, it will give SiO3 2 minus salt and water. This could be Na2SiO3 and water, but just depends on what the base is. In this case, it's NaOH, and it's supposed to be silicon oxide. All right, reactions with chlorine. Sodium burns in chlorine to give NaCl, a yellow gas, greenish. So basically, the observations are gray metal, and greenish yellow gas disappear, and white solid is produced. Remember to state that it's a gray metal and white solid because they're not transition metals and they do not form colored compounds. And since chlorine is used up, you can tell that the greenish yellow gas disappears. Similar to magnesium and aluminum. However, for aluminum, just state that AlCl3 forms, which can also form a dimer, which is Al2Cl6. You learn the properties of Al2Cl6 in chemical bonding, but Al2Cl6 forms at higher temperatures as compared to AlCl3. But whether you write AlCl3 forms or Al2Cl6 forms, I think you'll be given the mark regardless. Silicon reacts slowly with chlorine because silicon is unreactive as it has a giant covalent structure, and phosphorus will react slowly with excess chlorine gas to produce phosphorus pentachloride. These are just reactions that you need to know. All right, reactions with chlorine and water. Sodium chloride and magnesium chloride are ionic compounds and they dissolve in water to produce aqueous ion solutions, which can be written as Na plus Cl minus or just MgCl aqueous. Covalent chlorides are hydrolyzed by water. Please take note that they are hydrolyzed. We took note. This is different from oxides, which they form acids. Chlorides are hydrolyzed, so please take note of that. And AlCl3 has covalent character due to small electronegativity difference between aluminum and chloride. We'll get back to that you can look back to the chemical bonding videos or to get a better reference of that. But basically, these are the reactions. You have to memorize these. I know it's a bit difficult, but I don't have any form of mnemonic or technique to memorize this. This one makes sense to me. It's pretty straightforward. You can write 5H. This is supposed to be 5, not 3. You can write it as 5HCl or 5H plus and 5Cl minus, or you can just write it as 4H plus, 4Cl minus, or 4HCl. However, I prefer to write it like this, but you can write it in any way that you like. For aluminum, just remember Al H2O6 and 3 plus is the property, is the salt that's produced. All right, that's basically all we have for periodicity. However, I've not really put in a few details, which is reactions with water, which is pretty straightforward because we know that sodium will react with water to form sodium, and magnesium both react with water to form hydroxides. That's group 2, so I'll put it in that. Put it in a video which contains group 2 elements. So that's all we have for periodicity. I hope you guys understood everything, or you understood everything that I said. Thank you and goodbye.